Recording is rolling. It is Wednesday, November 30th. So the main thing today is going to be the second half of the Torque Lab. But before I get to that, a couple other things. I have returned your Momentum quizzes to your folder. So when you guys are back in the lab area during the lab later today, you guys can pick those up. You can still do corrections and then turn this in for partial credit back if you want, but those are back there. Another idea that I wanted to throw at you guys today, but not give you guys the full explanation, has to do with the gyroscopes. You guys play with gyroscopes? Right. I bet if you've ever like spun a top, right, and it like stays upright, but then when it stops spinning, it like falls over, or spun a coin, right? You guys try to balance a coin outside, it just falls over. But if you give this thing a spin, it'll like stay up because it has angular momentum. Well, something to do with that, right? Something to do with angular momentum. Right? Well, why doesn't it fall over? But can you guys see that this coin is like for something? Like it's like its axis of rotation kind of goes more like a little bit wobbly, right? And then there's some frictional forces that eventually bring it to stop. And this gyroscope works really good. See, I get one string pull, so I want to try with this guy. Look at that. Okay, so it'll stay upright. Of course, if the wheel wasn't spinning, it would just fall over. So going a bit off camera there, but it's still going, right? Of course, if it's spinning, it just falls over like that, right? Right, so what's the deal there? Also, I've got a picture of a bike wheel here, and I'm going to do the same thing with this bicycle wheel. Actually, I've got two of these in class. I don't know, have you guys got your hands on these yet? This would be a good thing to do today, right? I'll put this one back in the lab area too, and then give this thing a spin and try this out with each other. I want you guys to think about this, see if you guys can figure out like why it would have its property, like why it would stay upright. Now, how this picture is drawn, I'll do this off camera here. Does it look like it would be like falling over? Like this thing should definitely like fall down like this, right? Because it has some weight pulling down at this very short lever arm, so it should definitely have a torque, like a clockwise torque. It should definitely fall over, right? Here, here's the class. Here, see it like falling over, right? But if you give this thing a spin, it's gonna look like it's levitating. Right? Here, and I'll do this. You see it like levitating? But it's also processing at the same time. That's why it's like going around, like I said too, right? Yeah, so you guys can try this too when you get back there. Also, if you just hold it like this and then you try to turn it 90 degrees, if it's not spinning, you just turn it whatever. But if it is moving, you definitely feel like resistive force. It definitely does not want to change this orientation. However, if it's already spinning, you just want to keep doing that. So it has this angular momentum. Now, why would it have that resistive force? Why does this thing, here, let's get it spinning fast again, look like it's like levitating, like this? Great. Did you guys do that do that yourselves? What's got an explanation for that? So let's guys think about that for at least today. We'll come back to that later this week. But let's get to the main thing today, which is Torque Lab Part 2. So recap, let's do a quick recap of Torque Lab Part 1 from yesterday. Oh, here we go. Okay. So yesterday the setup was you guys had a meter stick, there was one spring scale, and then two lab weights pulling down. And you could shift these around and set up different equilibriums. Now, it was a really precarious equilibrium, right? If you shift anything like half a centimeter, the whole thing moves and fall over. But what we were showing was that you could pick any reference point. So I had you guys pick the scale as a reference point, and then later on pick the far end of the meter stick as a reference point, like and treat it sort of like a pivot point. Okay? And you can show the sum. If you sum the torque to zero, you can solve for stuff. I had you guys solve for what was one of the weights, right? And we got it at the end. Okay. Now today's setup is going to be sort of the opposite of this. This is going to be a more here. So there's going to be two spring scales pulling up and one lab weight pulling down. Now let's think about this. Do you think start from a forces point of view? Do you guys think that the total weight downward and the total weight upward have to balance out? Okay, that might actually be an easy, pretty easy way to approach this lab. I had to ask you guys like some question to give you guys something to solve for. So I don't know, maybe I could redesign this, but your target question is like, what is the lab weight? Suppose this was like a mystery weight, right? You don't know what the weight is. Okay. Now, obviously, you can get from dynamics to say, oh, well, if I just add the two spring scales together, whatever their readings are, that should be pretty close to it, right? Because the meter stick adds a little bit of weight, right? But do you guys think if you slide this weight back and forth, that the two spring scale readings change? Right? Like if you take this guy and you move it all the way to the right, you think that this one, the force going up, 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 up. Right? Oh, you know what? I'll show you guys a little bit different perspective of this. I'm going to switch screen here. Oh, so Paul Hewitt has a YouTube channel. So Hewitt Drew.
Welcome to the first of many Hewitt Druitt screencast lessons in physics. I'd like to tell you how my love affair with physics began after I gave up boxing and at the age of 25 began painting signs in Miami, Florida. Newly employed, I was assigned to paint with a painter who was unpopular with the other painters. His name was Burl Gray, who it turned out altered the course of my life. I remember one day when Burl was on one side of our scaffold and I was on the other side, he started twanging one of his supporting ropes. I show just one strand of rope here for simplicity. He said, "Hewitt, twang your rope." His rope went boing, and mine went boing. He said the ropes behaved like guitar strings, and the fact that his twanged at a higher pitch was evidence that the tension in his rope was greater than the tension in my rope. That made sense because Burl was somewhat heavier than me. Tension is the force within a stretched rope. Somewhat later, I'm walking over toward Burl to borrow one of his paintbrushes, and Burl says, "Aha, as you walk closer to me, will the tension in my rope increase?" And we both agreed that it would because his rope would be supporting more of our weights. Then he asked, "As the tension in my rope increases, will the tension in your rope decrease?" It seemed reasonable that it would, but Burl went further and asked if the tension in his rope increased by 50 pounds, would the tension in my rope decrease by 50 pounds? Or going further, if his rope increased by 50.1 pounds, would my rope decrease by 50.1 pounds?
What's the answer to that question? Yes or no? Yes, right? Yes, right? So their weights are constant, right? This guy's a constant weight. This guy's a constant weight. This scaffold beam that they're walking on has a constant weight. Maybe those, what do they add up to? The tensions that are holding them up have to balance that out. Now, this is going back a few weeks ago to just plain dynamics. If you look at some of the forces in the y direction has to zero out, right? The net force has to be zero because they're just at rest, right? Which is a type of equilibrium, right? But how can you figure out exactly what the tension in each rope is? Because as they're moving right and left, right, as this guy's walking right and left, the tensions aren't changing, but the sum of the tension has to still balance out the total weight, right? Right. So it looks like we can kind of start to set this up, but we're missing part of the story to be able to completely solve this thing. Okay. So here's a good snapshot. Okay. So you really need a system of equations to solve this. And one of those equations is the sum of the forces in the y direction of zero. Let's say that these two guys had it going upward has to balance with all the weight going down. It's supposed to have the like an apple or some object has some weight itself. Okay? And maybe the scaffolding beam has some weight. And I can treat that weight as if it's at the center of mass, which would be at like the halfway mark, right, going down. I know that these two guys down and these two guys up have to balance out. Tension up plus tension up minus these two weights down has to zero out. Right? You guys have known that for like many weeks in this class. You guys know that. Right? But what if you want to know exactly what each of these individual tensions were? And from that, you also need to know like the location of the apple, right? Because if you shift the apple around, if I move this apple to the right, what happens to this tension? It's going to increase, and this one's going to decrease. And if I move the apple back towards the center, now it goes like this, right? Right. So the other equation you need is a torque equation. The sum of the torque also has to zero out. Now this one is new to you guys as of a couple of days ago. Okay? So what you guys know from yesterday is you can pick any point as the pivot point. But usually to solve a question like this, you especially thinking ahead to college, if you guys get a college question one day, normally what you do is you pick one of the like these might be two unknown forces, right? You don't know either tension. You can pick one of those points as the pivot point, remember, you can pick any point, but if you pick, for example, this point as the pivot point, that's a really good idea because this particular tension, whatever it is, provides zero torque relative to that point. It's like if you treat this as the door hinge and you push right on the door hinge, it's never going to turn the door, right? Right? You guys got that idea? Right. Which means that you would only have one unknown in the torque equation, which would be the other unknown force. I guess that. So I set up a torque equation down here, and I actually picked this point right here as the pivot point. And how does that play out? Well, it plays out like this. Right? What this tension, whatever it is, times a radial arm of 0 meters from itself would provide 0 torque about that point. Right? 0 turning moment. Right? The weight of the beam causes a small clockwise torque. You guys get small clockwise torque, which is right here. The weight of the beam times L over 2. If the whole beam is L, this would be L over 2, right? Center mass of the beam. Right? The apple provides some torque. The weight of the apple times some distance x. You guys see that? Right? Weight times lever arm. Right? These are all at 90 degrees to each other. So sine of 90 degrees, just one. Right? Cross products. Right? And then finally, at the full length of the beam, you have the other tension. And maybe you could like solve for that, right? If you knew everything else, you could solve for that. The total torque has to still zero out. Now you have the system of equations, and now you can solve for the right, this tension, and then you can go back and solve for this tension. Okay, you guys get that? Right now, that's not exactly what we're doing today, but it's really close to. Right, it's like adjacent to what I'm having you guys do in the lab today. Okay, so you guys ready for today's stuff?
You put the equation back
Oh,
up.
yeah. Just see this. Oh yeah, this one is not in that printed notes page I gave you guys because I hadn't made this page by then, so I just this one's new. Okay, but that one is pretty good. That's a pretty good one right there. All right, guys got that? Oh, yeah. Take a photo. Good idea. All right. All right. All right. So let's look over at today's lab. All right, guys got that? All right, so today's lab. Let me zoom in on this picture, which does look a lot like that picture, except I moved these scales a bit from the ends, right? So they're in towards the middle a little bit. Okay? And the goal I'm giving for you guys is, I suppose there's like a mystery weight. We're going to find that weight using torque. Right? We're going to find that weight using only torque. Okay. So let me do this live demo in class because I basically got this set up. I got here this sort of flashes in front of the camera. I got meter stick, spring scale hooked to it. I got the slab weight. I got another spring scale on the other end. I bring this out and let's read some numbers and figure this out. This looks a lot like that picture, right? Right? So this weight is at the 60 centimeter mark, right? And that is a 1 kilogram mass. You guys see 1 kilogram? Now you guys know 1 kilogram weighs how many newtons again? 10 newtons, which is going to be the answer to this lab. So the answer is 10. But suppose it was like a mystery box, like I don't know what it is, right? Now, one way you can get it is you could just very simply add together the spring scale readings, right? And then that plus the meter stick would be pretty close, right? So this one I'm reading 3.4 newtons. This one I'm reading 6.7 newtons, right? So 3.4 and 6.7. And the 3.4 newtons is at 20 centimeters, and the 6.7 newtons is at 80 centimeters. So I got 20 and 80. Right, you guys see 20 and 80? Right, is that? All right, so let me run this example with you guys. So I'll do just like I did yesterday, run some example numbers, and then go back and have you guys make up your own and try it yourselves. Okay. Right, again, we've got two perspectives just like yesterday. So the first perspective is going to be, I'm going to treat the left spring scale as the pivot point. So that could be my pivot point right there, right? But again, it's a good idea because whatever this force is causes zero torque with respect to the point itself. So let's fill in these numbers. The left reading at the 20 centimeter mark, remember that was like 3.4 newtons. And I gave you guys a negative because we're going to define up as negative and down as positive. Okay. Okay. Since it is the pivot point, it has zero distance from itself and therefore causes zero torque. So you could have just ignored it anyway. Okay. Next line. Oh, the meter stick itself has some weight, and we're going to treat the weight as though it's acting at the center of mass, which is right here at the 50 centimeter mark. It's causing a small clockwise torque with respect to this point. Is that true? Small clockwise torque, right? Treating this as the pivot point. Right? Now, if this is at 50 centimeters and this is at 20, guess what is 50 minus 20? 30. You see a lever arm of 30 centimeters? So I've got The weighted mirror stick, I'll call it 0.1 newtons. That it's a little bit of an underestimate, but we're going to go with it. Okay. That's acting lever arm of 30 centimeters because 50 minus 20 would be that lever. So would that be 3 Newton centimeters worth of torque? You guys think? Great. Okay. Then the force on the right, remember that was 6.7 newtons, I said? So put 6.7, and it's going to be negative because of this negative, and I gave you guys a negative sign. Okay. And it was at the 80 centimeter mark. Remember, our pivot point is at the 20. So what's the difference between 80 and 20? 60. Ah, do you guys see a lever arm right here of 60 centimeters? So I'll put 60 centimeters right there. Okay. Let's multiply this together. What is 6.7 by 60? And it's negative. That's negative 402 Newton centimeters of torque. Okay. Oh, and I need to draw that in here. That's pulling counterclockwise with respect to this pivot point. Okay. Is that? All right, so we got this pivot point. This force causes 0 torque. The weighted mirror stick causes a small clockwise torque, and this spring scale on the right side is causing a huge counterclockwise torque. Okay. Now, the one I haven't messed with yet is the weight. Do you think this weight is causing a large clockwise torque with respect to this pivot point? You guys think? Right. Okay. Okay. Actually, sorry, I'm getting a little ahead of myself here. So this next box says to add up the 3 known torque values. Right, so 0 plus 3 plus negative 402. Is that positive or sorry, negative 399 Newton centimeters? Do you guys think? Right. This plus this plus this. Okay. Now that's all the torques except for this torque. Ah, so what does this torque have to be equal to? For all the torque to zero out, it must equal positive 399, right? Right? Isn't that what that is? Okay. Because these three guys sum to negative 399. So this guy must be positive 399. So it all zeroes out, right? Right. That's what all of this bit says here. And the weight was located at the 60 centimeter mark. So 60 compared to 20, what's that lever arm? Yeah, so 60 minus 20 is 40, right? So if you have 399 Newton centimeters of torque, so here's torque goes R cross F, right? Okay. And 40 centimeters out, divide those two, get the force, which is 9.98 newtons. Oh, which is the 1 kilogram lab mass weighs 10 newtons, right? Guys go there? It checks out. Okay. So that's one way to solve this. Is way you can solve this using torque, right? Then the left side of this paper could be the exact same configuration. Notice the picture didn't change. What does change is your perspective. I'm going to redefine the pivot point as being at the 0 centimeter mark. So here's your new pivot point, right there. Okay. Now, relative to that new pivot point, which has shifted a little bit, about 20 centimeters off from what it was before, it looks like this left spring scale is now causing a small counterclockwise torque. The weighted meter stick itself would be causing a small clockwise torque. The lab weight is causing a large clockwise torque, and the spring scale on the right is causing a large counterclockwise torque. Wouldn't that have to be the case? Right? Of course, those 4 torques have to zero out. So we'll do the same thing we did before. We'll do 3 of those, and then the 4th one must zero it out, and then we can solve the weight. Okay. So the left force reading was exactly the same as what it was before. I just take that number and copy paste it right here. 3.4 newtons, and I'll call it negative. Okay. But now the location perspective has changed. So it's 20 centimeters out. So I'll call this 20 centimeters because this lever arm is 20 centimeters centric. Okay. So what is 3.4 by 20? 68 Newton centimeters. Oh, sorry, negative 68 Newton centimeters. Right. The meter stick weighs 0.1 newtons. That didn't change, but now it's at 50 centimeters out, right? This full lever arm. So that's what, 5 Newton centimeters of torque, right? That's clockwise, which I'm calling positive. Then the right spring scale, well, that also doesn't change. It was negative 6.7 before, it's negative 6.7 now, Newtons. It's Newtons. But its position, well, it was at 80 centimeters out, so that's the full lever arm from this endpoint. So I'll put the full 80 centimeters in there. So what is negative 6.7 by 80? That is negative 536 Newton centimeters. Okay. You guys have that? All right. Okay. So if you add up these three torques, get negative 68 plus 5 plus negative 536. I'm getting negative 599 Newton centimeters. Okay. Now that's just this guy, and this guy. I skipped over the weight. Okay. Now if these guys collectively are negative 599, then what torque is caused by the weight? Yeah, positive 599 because it has to zero out. So it's 599 Newton centimeters for the weight. That's the torque it's causing. Okay. It's at 60 centimeters out. So I'll put 60 centimeters for the radius. Okay. And then if torque is equal to R cross F, I'm going to take 599 divided by 60. Okay. It looks like 9.98 Newton. Ah, look at that. It's the same thing we got before, just from a different perspective. So it's a different path through the woods, but it gets to the same location. Okay. Guys good there? All right, so yeah, everything you need, back the ladder, walk around, help you guys out. The bike wheels will be back there. You guys can think about angular momentum and just turn this into the grade tray by the end of class.